Okay, it's 3:40, so we're going to get started. Welcome, everybody. I hope you're all doing well and everybody's healthy. I just wanted to remind you, I'm recording this Zoom session so that we can post it on the website later, as we have done with the other lectures. So if you need to go back and review something, you can find it on the website, or you can tell your friends that are in the class who couldn't make it now can view it later. I just wanted to remind you that you're welcome to turn on your cameras if you want, but it's not necessary. Also, like to be able to take questions during the lecture. So as usual, you can do that by raising your hand in the Zoom app, which I think you find under the Manage Participants. And or you could just speak up if you want, or you can send me a chat message and I'll try to watch for chat messages. Okay, so I think we're going to get started. Today we have a lot of good stuff to talk about. We're going to talk about memory circuits and memory blocks. So here's an outline of what we're going to talk about. There's first, I'm going to have a section where we talk about the circuits that make up memories. And here we're talking beyond just flip-flops and registers. We're going to talk about when we collect together large amounts of state into one block, okay? And then after we talk about circuits, I'm going to talk about memory blocks and how they're used, okay? So multi-ported RAM, how we combine memory blocks, how we build FIFOs, what the memory resources are at FPGAs, a little review about caches, because caches these days one of the primary uses for memory blocks. And then I'll end with a couple tips about how to think about memory blocks and how it relates to your project. So here we go. So first, some memory classifications, just to kind of define some terms. So when it comes to large memory blocks, it really come in two different forms or two different styles. There's hardwired memory, which is read-only memory. So this is memory that can't be changed. It's typically configured, or the contents of the memory is determined when the chip is fabricated. Okay, so this is read-only memory. You can't write it. We're really not going to talk about that here. We're going to talk more about programmable memory, and this is read-write memory. And really comes in two forms. There's volatile and non-volatile. So what volatile means is when the power is turned off from the chip or the device, the memory loses its state. Okay, and this has two prevalent forms. There's SRAM, static random access memory, and DRAM, dynamic random access memory. The static memory uses positive feedback in a way very similar to the flip-flops to hold state. And DRAM uses capacitive charge, which we haven't talked about much yet, but we'll talk about that today. Okay. So this is what we're going to focus on today, is the volatile memory. There's also non-volatile memory, and this is memory that has persistent state even when the power is turned off. And you know about this. This is flash memory. For instance, it's in all cell phones these days, and iPads, and all kinds of devices use it as a way to hold state. And these days it's used also instead of hard drives, even on laptop computers, as you know. Again, we're not going to talk much about that. A lot of the same principles that we're going to talk about with SRAM and DRAM apply to flash memory and non-volatile memory, but it's a little more specialized and requires special circuits to make it work. Okay, so here we go. We're going to talk about memory circuits first. So as I mentioned a minute ago, there's two primary forms. There's static memory and there's dynamic memory. And the principle behind static memory is shown here on the left side, where we have a pair of inverters that are in a feedback loop with one another. So this uses a restoration to hold the charge, or hold the value. So as long as the power is on, if there's a 1 here, we'll have a 0 there, which will make a 1 here, which makes a 0 here. If anything disturbs one of these sides, like some noise that comes from noise over power supply or some other signal couples to this, or there's an alpha particle, something hits the chip, this circuit will restore it back to its good value because of the restoration property of these inverters. So it's very robust as long as the power stayed on. Of course, we have to deal with how do we change the state here, and we'll talk about that in a little bit. Dynamic memory uses a different principle. It uses the storage on a capacitive node. So for instance, in this simple circuit here, if we charge this capacitor up to a 0 or to a 1, it will hold that value for a while. Eventually it'll leak away through these transistors and other mechanisms, but it will hold the charge. The leakage is somewhat dependent on temperature, as we talked about last time. In fact, it's exponentially dependent on temperature. So this works better when chips are not hot. It's the principle that's used behind dynamic memory. In the old days, when I was a grad student designing chips, we actually built latches this way, where we didn't have feedback. We would just build a latch as shown here in this picture. You'd have a transmission gate, and you could store up a charge in a capacitor, and as long as you changed it before it leaked away, this could be a reliable way of creating a register. We tend not to do that anymore. It's very prone to noise. It's not very robust, but it is dense. It's much smaller, fewer number of transistors, as we'll see when we look at the DRAM circuits, and therefore it's hard to get it right, but it's so dense and so cheap to build memory this way that we have DRAM circuits that can be made robust. And I'll talk about what we do to make them more robust later. Okay, so those are the cells. Now, the basic mechanism is shown here, and both those mechanisms can be used to build an array of high density memory. Right? And when we build an array, we have what we call a memory block. And this is kind of a generic architecture for how memory blocks are put together. You can see in the picture on the right. So there's this core area here where we store a lot of bits of storage, lots of bits to be stored in a two-dimensional array. And then there's some periphery circuits that are used for reading and writing those bits. Right? So we're going to talk about the operation later, but I want to define some of the kind of important aspects of this architecture. There's word lines, and these word lines extend through the array. Right? And a word line is used to select a row for reading or writing. So it's like an enable line that extends across the whole row here, okay, and allows us to either write or read an entire row in the memory array. Then there's the bit lines, and the bit lines are used, they go in this direction in this picture, vertically, and those are used to carry data from or to the periphery. So from the periphery if we're going to write the value of a cell, and to the periphery if we're going to read the value of a cell. Right? Typically, we read or write a whole word at a time. So we'll send a whole series of signals up into the array, and then enable the proper row to have that be written. If we're going to read, we'll enable the proper row, and those cells somehow will send their data down on the bit lines, and then it can be sensed and on the periphery here. Okay, so then this core, typically we make the aspect ratio, meaning the ratio of the width to the height, to be close to 1. Otherwise, what that does is tend to balance the delay on this word line and the delay on the bit line. So there's delay associated with that wire and this wire, partly because of the capacitance of the wires themselves. But as we'll see, these wires connect to the bit cells, and every place where it makes connection to the bit cells, there's added capacitance there. So, and there's a lot, and typically a fair amount of bit cells in this direction and in this direction. Therefore, that's a highly capacitive line. So to kind of optimize the delay associated with the sum of the delay on the word line and the bit line, we tend to kind of balance those out and make this relatively square. Right? And then there's address bits, and the address bits are used to address some particular word in the memory. There may be more than one word per row. So the bit lines, or the address lines, get divided between a decoder here on the side, which is used to select some row, from the address. And some of the address bits will be used down here to select a set of columns, to select the proper word out of a particular row in the array. Okay, we'll talk a little bit more about that later. And so there's a row decoder. What the row decoder does is take the address, some of the address bits, and generates a one-hot code, meaning it activates one of these rows. Likewise, some of the other bits are used to activate some subset of columns. So we could kind of multiplex out the proper set of bits for a particular word that's stored in a row. Okay, and so this architecture kind of works for both SRAM and DRAM. It's the same basic idea. So it's a basic block. Now, a large memory like a large DRAM would be made up of many of these blocks. Likewise for static RAM. So, and I'll show a picture of that later, but we'll put a bunch of these blocks together to make a bigger memory. Okay, so that's the basic architecture. Now I'm going to look at the circuits. So first SRAM. So the bit cell that we use for SRAM, as I mentioned earlier, uses this property of cross-coupled inverters, where we can use the restoration property of the inverters to keep a very robust storage of 1 or a 0, depending on, it'll store either a 1 on this side and 0 on that side, or a 0 on that side and a 1 on that side. Right. So the value is actually held differentially. We have both versions. We have B and B bar, right, in the cell, which is nice, and we can use that to our advantage to make the circuit simpler. So that's the basic storage, and then we complement that with 2 extra N-FET or N-type transistors, and we call those the access devices because they're used for accessing the cell, as I'll describe in a few minutes. So here's the cell in more detail. I've just expanded the circuits for the inverters here, and you can see there's the VDD node, there's a ground node. This is a word line that moves through the cell, and it's connected to the gates of these 2 access devices. Right. So when this particular row is selected, this word line would be activated, be high, which would turn on these pass transistors here, these N-FETs, which then connect the cell to the bit lines. And the bit lines are used, as I said, to carry the data down to the periphery, or in the case of a write, to carry the new data from the periphery into the cell. You can see here the cross-coupled connection. This is one inverter here with its input. Its output goes over to the input of the other inverter, and that output of that other inverter comes back to the input of the first inverter. So that's how we get the ring. And then these access devices are used for sensing the state of the cell or for writing new value into the cell, as I'll describe in a minute. Just so you see how this works out in layout. Well, okay, this is how then it looks if we put it into an array. The cells are stacked into a 2-dimensional array to form the core of the memory. Right? So these cells here are common for one row, and then these cells here are common for one column. So the rows in a column all share the same bit line, and the rows in the column all share the same word line, because we activate all the rows, all the bit cells in a row together, and then each cell will send its values down on the bit lines. And since only one row is activated at a time, this is kind of like a tri-state situation where only one driver, in case of reading, is using the bit lines. All right, so they can share it because only one row is. So all the bit cells in a column can share the same bit lines because there's only one that's ever active at once. Okay, so I wanted to show you what the layout looks like if you look down the surface of the chip, or at least the layout that we generate for manufacturing. This is an SRAM, this is typically called a 6T or 6-transistor SRAM. This is the configuration I showed you a minute ago. And this is kind of an older layout style, but you can see it's kind of interesting here. The challenge in laying out the cell is getting this cross-coupled connection here. But you can see the 2 inverters. That's the P-type pull-up That's the N pull down for an inverter. That's a P pull up and N pull down for the other inverter. You can see the output of this inverter is on metal, which is blue, metal one, first layer metal, and it comes here, connects the drains of the two transistors together, and then comes around here and goes over and connects to the polysilicon here, which is the drain, the gate connection for the input to this other inverter here. And the output of that inverter is on metal one also here, first layer of metal, connects the drains of those two transistors together, and then comes back around and connects to the input to the other inverter over on this side. And then this connection here is for VDD, and then this connection here is for ground. And then here's the word line, and this layout comes in polysilicon, and that's used to form the channel of the transistor here at one access device, and there's the other access device. So these are N, all of the N FETs are down here, and the two P FETs are up here. And then the word line, which is in purple here, is running, you can see two, I'm sorry, the bit lines are running in purple here. It's those two vertical wires. So that can make a pretty dense thing. So these get tiled together, right? And the VDD just runs through all the cells. And then this VDD can actually get shared for the cell above it will get mirrored and share the same VDD. And then of course the bit lines get shared within a column, and the word lines get shared across the row. This is a more modern layout style, which is quite popular these days. It just works out a little better for modern processes. And you can see the pull down here. There's the access transistor. There's the pull up. So in the center, we have the N well here. And inside the N well, we form the two P transistors, which are the two pull up transistors for the inverters. And then there's an N here, N region here, N transistor region here, two transistors, the access transistor, and then the pull down for the inverter. Same thing over on this side. And then the bit lines you can see here coming down through here, and the VDD in this configuration also runs parallel to the bit lines. This is what it looks like after it gets fabricated. You can see all these nice sharp edges on the rectangles get kind of smoothed out, right? Because this is all very fine geometry, fine processing, right? So it barely works, but it just works. We get enough of a width here to actually make a real transistor. Okay, so that's kind of how it works out in the layout. So we're going to talk now about, for this cell, this 6T cell, SRAM, what the operations are involved for reading and writing values out of the cell array. Okay, and so here's the read operation first. So the first thing that happens, and it's a fairly complicated thing. It's more complicated than just reading a register because there's many cells put together, right? And the priority for memory blocks is you want as high a density as possible. That usually means it complicates the periphery, the circuitry around the periphery a little bit, but that's a relatively small part of the whole area. So the idea is to get as many bits as possible in a small area, and therefore we pay a price in a slightly more complicated process for reading and writing. So the way this works, and there's a little controller that will control the read and the write operations. And so the first thing it does is pre-charge the bit lines. Bit lines are pre-charged to VDD, which means we force both bit lines to go to VDD. Right? That's while the word line is low. Okay, so all we do is charge up all the bit lines across the whole array to VDD, and that can be done by just turning on a P-type transistor that pulls them up. And there's enough capacitance on those bit lines then we can turn the precharger off, and the bit lines hold their high value. Right? They'll take a while before they would discharge. Okay, but right after the precharger is turned off, the word line is driven high, the proper word line. So the decoder will, previously will have been decoding the address, so it knows which row we're trying to access, right? And then there's a driver on the output of the decoder, that'll be turned on according to this controller, which will cause some particular word line to be selected. Okay, so now we're looking at the row where the word line is high. So that will turn on these two transistors here, access devices. And what will happen is the cell will pull down on one of the lines, right? So you notice we don't have P transistors here. These are not transmission gates. They're just N-type transistors, which means they're really good at pulling down. They're not so good at pulling up, but we don't have to pull up because we've pre-charged the bit lines high, right? So then whichever side of the bit cell is holding a 0, that means the pull down in this inverter is conducting. That will then discharge the bit line down through this cell, right? So effectively, we transfer the 0, and you can see it here. The VDD, the ground, the voltage on the bit line will start dropping down, right, as this cell starts discharging the bit line here. The other side, in this example, is holding a 1, and we can turn on that access device, and there's no voltage across it, so nothing will happen. No current will flow. So that will stay at a high voltage. Right. So there's a couple issues here. One is, and then I should say, if the cell was holding an opposite value, if it was holding instead of a 0 on that side and a 1 here, we're holding a 1 and a 0 over here, then the opposite side of the cell would do the work, meaning it would start to pull down and this side would just stay high. So from looking at the bit lines down at the bottom of the array, we can tell what the value was that was being stored in the cell. We're effectively transferring the value from the cell to the bit lines. Now, there's a couple problems. One is these transistors, to make the memory as dense as possible, the transistors that are inside the bit cell in these inverters is relatively small. And these bit lines, since they connect to a lot of cells, as I mentioned before, they are a large capacitance. So it takes a lot of charge, a lot of time at a small current. This inverter, since it has weak, small transistors in it, it can only sink a small amount of current. So it would take a long time to discharge this bit line all the way because it's such a big capacitance. Okay. So we have circuits on the periphery that can speed up the reading, and I'll talk about that in a little bit. The other problem is that during the read, this Q bar node, this internal node here, it's going to get slightly pulled up, right? Because what will happen is when this access device gets turned on with the word line, right, there will be a net positive charge voltage from this point to this point, right? So current will start flowing through here, and it'll start charging up this node, right? And it'll take a little bit of time while this inverter starts sinking that charge. So it's going to push up the voltage on this node. So there'll be a little voltage bump. So when the circuit's designed, we have to size the transistor so that little voltage bump will never exceed the threshold of this inverter here. If it does, it'll flip that inverter, and then the whole cell will accidentally flip. We don't want to flip the value stored in the cell in the process of reading it. Right? So we can achieve that by making sure that the pull down transistor in this inverter here is much stronger than the access device. Right? So it kind of puts a constraint on how we design size the transistors in the cell. But it's possible to do that, and it's done all the time. Okay. And people who design these cells for a living use SPICE models and other ways to verify that they have the right sizing of the transistors. Now, so that's how the read operation works. The write operation is pretty simple. What happens is there's a column driver circuit, which on the periphery, so connected to the bit cells at the bottom of the array, there's a circuit that can drive a one on one bit line and a 0 on the other bit line. So we mean by drives it differentially. So if we wanted to change the value in the cell from holding a 1 and a 0 here, this side we're calling Q bar, it's arbitrary, but let's call that Q bar. So this cell previously was holding a 0 because Q is 0 and Q bar was 1. And if we want to change its state, we could drive this bit line to a 0 and this bit line to a 1, and then turn on the word line. And what that would do is force the value into the cell here. Okay. Now, for a successful write, this access device has to be able to overpower the internal node on both sides, right? So if the cell were holding a 1, that meant the p-type transistor here was pulling that node up. So this device has to be stronger than that p in order to overpower it. Okay, so that puts another constraint on the design of the cell, which is the ratio between the p-type transistor here and the access device. Right, that would be to make it a 0. Okay, so that's how the reads and the writes work. Okay, with SRAM. So, and the reason it works out well is we really have differential bit lines here. Okay, so both reading and writing, we read both bit and bit bar, or Q and Q bar, and writing we drive Q and Q bar. Right? And that allows us to get away with just one type of transistor here and have it work effectively. Okay, so that's SRAM. I'm going to talk about the periphery a little bit, what we put around this array of cells in order to make it work. So here we're back to our picture. So we were just talking about the individual storage cell here and how it works in the context of the cell array. The other circuits around it, I've mentioned the decoder already, and there's sense amplifiers down here, which we use to help speed up the reading. And then there's controls and timing circuits, which I'm not going to talk about in detail. And there is, I didn't put it in my list, but there's this column decoder down here, which we use for choosing a particular word from the row. All right. So first, the row decoder. Okay. So there's a lot on this slide, so I'm going to spend a few minutes on it. So here we're assuming that we have L total address bits. Okay. We have K of those address bits are used for column decoding down here. We have L minus K, which I use for row decoding, right? And so what the row decoder does is it takes these L minus K address bits, right, and expands that to those address lines into 2 to the K minus 1 lines. These are the 2 to the K minus 1 word lines here. Right? And that's the purpose of this decoder here. Here's an example. Let's say we're going to look at the row decoder for a 2K by 8 memory block. So when I say 2K by 8, that's the standard way of saying that this is a memory that has 2,000 or 1,000 is 1024, has, sorry, 8K by 8, has 8K words of 8 bits each. Okay, so the by 8 means the width of the memory. So this particular memory configuration, we're assuming has, in this example, has 8-bit words. Okay, we could imagine 16-bit words or 32-bit words, or even 1-bit words if we wanted to. Okay, for this example, I'm saying 8-bit words. So the total capacity of the memory would be 8K times 8. Right, AK is 2 to the 13, and 8 is 2 to the 3rd. So the total memory capacity for this would be 2 to the 16th bits, right? Now, in order to make this cell array square, this would be one way to arrange it. We could arrange it 256 cells by 256 cells. That would give us our total number of bit cells that we need. Right? That would mean that each row, if it were 256 bits, it would have 32 of these 8-bit words. Right? So you can imagine words 0, 1, 2, 3, 4, 5, 6, 7 are in the first row, and then 8, 9, 10, 11, 12, etc. are in the next row. So they're all lined up in there one way or the other. I'll show you how we line them up later. Okay, but for now, imagine that putting multiple words per row here. Okay, so that would keep it kind of square because we'd have the same number of rows as we have columns. And if the bit cell were approximately square, that would make an approximately square cell array here. All right, so we'd end up with something like that. Okay, so that means this 2 to the k minus 2 to the L minus k, that number would be 256. Okay? So here's some more details. In this case, we'd have 13 total address bits because that's what we need in order to address one of 2 to the L or one of 8k words. Right? It's 13 is log base 2 of 8k. In this example, k would be equal to 5, right? Because we have 32 words per row. And k tells us how many words per row, right? L minus k is the leftover address bits. Those are the number of rows, which would be 8. And so 2 to the L minus k is 256. Right? That would tell us how many rows, okay? So, so that tells us what this decoder has to do. This decoder has to take 8 address bits and generate 256 outputs. Only one of those would be high at a time, right? And the one that's high corresponds to a particular row that's being accessed, right? So the address comes in, these L total address bits, the L bits are used to address some particular row, some particular word in the memory, but we have to break that up into first addressing the proper row and then addressing the proper word within that row. And that's why we split them between these two decoders here. Okay, so row decoder, what does a row decoder have to do? Well, it's like any other decoder. We've been talking about decoders all semester. And the only difference here is that typically they're big. There's lots of outputs, right? So here's an example in this slide for 10, if we had 10 address bits, right? The output of the top of the first row of the decoder, right, would be the one that selects when the address is 0, and it would activate the 0 row. And then the bottom row would be the one that is activated when the address is the maximum. It's 511 here. We're missing there should be a bar over all these. Sorry about that. Right. Now, so it kind of looks like this, right? There's effectively an AND function for each of the rows of the array. So it takes the address in, and it just kind of does a pattern matching between the address here to activate one of these outputs. So we can do that easily with NAND gates. They'd be very large NAND gates, for instance. For this memory array that had 512 rows, we'd have to have 10 inputs into these NAND gates. So we have to find a way to make it a little more practical. And by the way, we can use NOR decoders as well by using De Morgan's law. We can just invert this function and assume that we have an inverter after the NOR gate, right? And so then we could use NORs instead of NANDs, right? So this is effectively a collection of 2 to the k logic gates, but where k is the number of address bits going into the decoder. But we need it to be dense and fast, so we use some tricks to make it dense and fast. So the usual technique is to use pre-decoders. And the idea behind the pre-decoder is the following. If you look at this picture, this illustration on the left, what this shows is the functions that we want to evaluate for each output of the decoder, right? So this says when the input is 0, we activate this output. When the input is 1, we activate this output. When the input is 2, we activate this, et cetera, et cetera. So these are kind of like the min terms of this function, but So as I said before, this could be implemented as an AND function for each row here. If you look at this, there's a lot of redundancy in here. Right. For instance, in the top 2 bits here, you can see this pattern where the top 2 bits are all inverted, right? And if we continued looking down here, we'd see another pattern that repeats itself 8 times in this example. Likewise here in these 2 bits, there's this pattern here where they're all barred. And then that actually will appear again once more. And then this pattern here, that will appear twice. And then on the low 2 bits, we'll have these repeating patterns that keep showing up. Right. So there's a fair amount of redundancy in this decoder function, right? So it would make sense to try to make it cheaper. It would make sense to try to factor out those common terms and compute them only once and then share them wherever they're needed. Right? And that's the principle behind a decoder. And the way we actually, pre-decoder, the way we do that is, in this example, I used pairs of bits. For instance, we can take a sub 1 and a sub 0 and their complements. And from that, we can generate 4 signals, right? Which is kind of a decoding, right? Of these 4 signals here. And one of these will be activated depending on the combination of A0 and A1. So that'll be a 1-hot encoding. Okay, we can do a similar thing for A2 and A3 and for A4 and A5. So we decode these in smaller groups and then use the decoded versions of these signals for the next level of decoding. Right, and I'll show you that on the next page. So here's the circuit for that example. So we use A0 and A1 and their complements. Those are these 4 signals here. And we form all combinations of those. And those form a 1-hot code here, 4 different signals here. And only one of those will be activated depending on the value of A0 and A1. We do the same thing for A2 and A3, and then same thing for A4 and A5. And then the final decoder is just a series, in this example, of 3 input NAND gates, where each NAND gate picks the proper signal from the pre-decoded values, right? So each output is a unique combination of the pre-decoded values. And so this then is simpler here. We only have 3 input NAND gates. And we have a lot fewer gates because we share these kind of pre-decoded values among within all the gates of the final decoder. So, okay, so that was, oops, sorry. Go back, yeah. All right, so that's the idea of pre-decoder. And this helps make it fit and be small and be fast. So that was this row decoder. Okay, so that choose the proper row. And then once we have the proper row selected, we have to, and that gets sent down to the bottom of the array. We have to choose the proper word out of the row. Okay, and so this is there's actually, we call it a column decoder, but it actually has the function of a decoder and the function of a multiplexer. It has to multiplex out or choose the proper word out of the row to send it to the output. And so if each row has 2 to the k words, we assume here each row has 2 to the k words, and each word is m bits wide. So we have to somehow find a way to store the 2 to the k different words in this row, right? And typically they're interleaved. We could put word 0 here, and then all the bits of word 1 there, and then all the bits of word 2 there, etc. But that would create a very complicated multiplexer down here. We'd have large collections of wires that would all have to come together and get multiplexed. It's more efficient to kind of do it in a distributed bit way, and so they get interleaved. So and I show you that on the bottom here. Here's an example. If K were 2, meaning we have 4 different words in a row, and each word was 8 bits, right? My 4 words are A, B, C, and D, and I distribute the bits of each, interleave them. So first we put all the 0 bits from all the words, then we put all the 1 bits from all the words, and then all the 2 bits, and then all the 3 bits. So A is actually spread out. The bits of A are, there's A0, there's A1, there's A2, there's A3, there's A4, etc. So the word gets spread across the whole array, but then they all get interleaved. This makes the circuitry on the bottom simpler, because once we have those distributed in this fashion, we can build this type of structure. Here, in my example there, we had four words. All right, so we use this thing can be repeated for across the array. So we have 4 words, and we can repeat this as many times as there are bits in the word. Right? So locally we have all the 0 bits, and so depending on, we have a simple NOR decoder here, and we just choose to activate one of these transistors, and that will choose the proper word. In this case, the ith bit of the proper word, and this structure gets repeated for as many words, for as many bits as there are in a word, and they can share these select lines. So it's kind of a way to build a distributed multiplexer. This one doesn't show the differential signaling. The actual circuit, this is just a simplification. In the actual circuit, it would have bit and bit bar, both signals going through the multiplexer. Okay. So this is a nice way to do. So once you do the interleaving, and then we can use a simple multiplexer for getting the signals out. Okay, and the last part of the periphery, excuse me, that I want to talk about is the so-called sense amplifiers. And I'll show you where they are. They're in this picture here. They're part of the reading operation. And I told you earlier that when we activate a bit cell, it has to be, it's a very small transistor in here that's trying to discharge a bit line. And it's going to be slow going. If we waited for it to get all the way down to close to ground, it would take a long time for that to happen, because there's a lot of capacitance and a small amount of current. Relatively large resistance in that pull down. So we use a sense amplifier that can help speed up the reading operation. Right? So as I said before, this capacitance is large. This current is small. The time is proportional. I guess you've seen this before. The time of changing the voltage on, or changing the value on the node, is proportional to C and the voltage change that we'd like to make divided by the current, because we're using this current to discharge this, and the dV tells us how much change we want to have. So the C is large because the array has lots of cells connected to it. The I is small because we'd like to make the bit cells as small as possible. So we can't really do much about those two, but what we can do is to live with a very small change of voltage. Right? And the way to live with a very small change of voltage is to use a sense amplifier. And a sense amplifier is a special circuit that can take a small voltage change and turn it into a large voltage change on its output. Right? And because we can do this effectively and reliably, because we have differential signals. We have B and B bar. Right? So a typical way to do that is to use an amplifier that's shown here. This is a differential sense amplifier. If you've ever taken an analog course, you should recognize this. It uses a differential pair here with a current source and some pull-ups. This is really a classic differential amplifier structure. It's a basis for operational amp, if you're familiar with those. If not, don't worry about it. It's just a circuit that can take a voltage difference between B and B bar and produce a large voltage on Y. So if there's a small positive voltage between bit and bit bar, Y will be close to VDD, and if there's a voltage going the other way, opposite direction, Y will be close to ground. And then we put it through an inverter to clean it up. Okay, so these test amplifiers are used, and the output is sensed at just the right time after the word line is turned on and the voltage on the bit line starts to change. Okay. And this is how it looks in context. We have, this is one cell that's being read here. And here, the bit lines come all the way down. Of course, there's more bit cells here, not shown. And the sense amp is here used to amplify the difference between those bit lines and provide a good output. This stuff on the top is the precharger. That's what's used to precharge the bit lines before the word line is activated. And there's a transistor here that equalizes the charge. And then there's some P-type transistors that pull these up to VDD. And then oftentimes some P-types, weak P-types here that are keepers. They're here to help preserve the charge when the precharger goes off. Okay, so that's SRAM. Just check the time. Okay. So we're not going to finish memory today. We'll work on it. We'll get to it after the break. So the nice thing about SRAM is this is all built up. Even though we use some analog circuit techniques, like in the sense amp, for instance, we can build this easily out of standard transistors that we use for logic circuits. Right. So this is the SRAM is the type of memory that you'd see most common in chips like microprocessors and other signal processing chips, GPUs and the like, because if we need a large amount of memory on chip with the processor, like for instance, cache memory or register files, perhaps we can use this type of memory because we can build it out of standard transistors, the same types that are there for building the logic circuits. It's a little dense, it's less dense than SRAM, DRAM, as we'll see. DRAM is a memory technology that's usually is not combined with logic circuits because it requires a special process in order to make it very dense, as we will see. Okay. And DRAM relies on the principle of capacitive storage rather than feedback. Before I show you the most common type of DRAM, though, I'm going to show you this 3-transistor DRAM cell. Remember, the SRAM was 6 transistors, so this will be smaller than the SRAM cell. So it has the advantage that it's smaller, but it has some disadvantages too. Now, this particular cell, DRAM, is a type of DRAM that can work in a normal logic process. Can be made out of standard transistors. But it's not the type of cell that's used in a commercial DRAM. Right? But it's interesting nonetheless, so let me just describe how this thing works. So you've got 3 transistors here in this configuration. There's 2 bit lines and there's 2 word lines. This one is not differential. All right, so this bit line is used for writing values into the cell, and this bit line is used for reading values out of the cell. And these 2 bit lines, there's one for writing and one, which is top one, and then the bottom one's for reading. So this cell, it works in the following way. If you want to write a value into the cell, you drive the value onto this blue bit line here on the left, and then turn on the right line, or right word line, sorry. That turns on this N-type transistor, and the value can go through the transistor into the cell, and it gets stored on the capacitance of this M2 here, this device. And then the right word line would be turned off, and this cell will store this charge on this capacitance for a while. As I said earlier, it'll leak away eventually, and it's somewhat temperature dependent, and it's probably the order of tens or hundreds of microseconds. But if the cell is going to be rewritten or read quickly enough, that's okay. It would have to be recharged from time to time so it doesn't lose its value if it's going to hold its value for a long time. To read it, what you do is turn on this read word line, and that turns on this device here. And after previously pre-charging the bit line too, so we can pre-charge it high, and if the cell were storing a 1, it would pull that line down through these 2 transistors. If we're storing a 0, then there would be no change in the bit line. Right? And on the periphery, you can sense whether or not there's a 1 or a 0, and can use that to determine what was in that bit cell. So one issue is that the nice thing is reads are not destructive, just like with the SRAM cell. There's no constraints on the device ratios like we had in the 6T SRAM cell. One disadvantage, as I mentioned, which is typical of all DRAM, is that we're using capacitance to store value. And if we wait too long, this value will have leaked away. So if we're not going to read it for a while, we're not going to use it for a while, we have to read it occasionally and just write the value back in order to refresh it. The other issue with this particular cell is that there's a single transistor here for writing. So if we write at 1, we can write it, we'd end up with VDD minus VT in the cell, right? So it has less noise margin. This will be a weak 1 here. Okay, it's probably strong enough to turn on this NFET device so we can still read the value, right? But it's going to leak away even faster than we thought. 0 is a good 0 though. Okay, so that's 3 transistor cell. That's been used to some success in a variety of chips, and it's denser than the 6T SRAM. Now, the more common type of DRAM cell is the so-called 1 transistor DRAM cell, 1T cell, and this is the one that's used for most DRAM chips that you see these days. And it's kind of interesting. There's 1 transistor and a capacitor. And the capacitor here, there is some capacitance associated with the this region of the transistor, but because we need a lot of capacitance here, it usually uses a special capacitor that's built for each cell, and the capacitor is built using special processing steps for the special IC process that's customized specifically for DRAM. Okay. So once we do that, we have a capacitor here and a transistor here, and this transistor is used for reading and writing. Again, it's used for accessing the state, which is stored on the capacitor. So the way it works for writing, this C sub S, this C storage, is charged or discharged by, again, activating the word line and then the bit line, right? So we turn on the word line and then drive either a 0 or a 1 onto the bit line, and that will get transferred into the cell because the word line will have turned on that device. With DRAM, sometimes this voltage on the bit line is boosted above VDD so that we get a good high voltage here. We could boost, if we boost the right voltage to VDD plus VT of this transistor, then we can get VDD on that bit cell, if that's important to do. And I think some DRAMs do that. Now, reading is tricky with this cell because we don't have an active device to help do the read like we had in the 6T SRAM cell and the 3T DRAM cell. So we rely on a charge sharing principle, okay? And the way that works is we'll typically pre-charge the VDD, the bit line to around VDD over 2, right, about halfway, and then turn on the word line. And what will happen then is this will charge share between the bit line and the capacitor, the bit line capacitance and the capacitor that's inside the DRAM cell. So if the capacitor here is discharged, it's holding a 0, some of the charge from the bit line will come through, and they tend to equalize themselves, right? Because the voltage across here will cause current to flow, right? So what we'll see is if the bit line was charged to VDD over 2 and this was holding a 0, when we turn on that transistor, the bit line voltage will drop a little bit because some of the charge that's keeping it at that voltage will migrate over to that transistor or to that capacitor. Likewise, if the cell we're storing a 1 and we turn on that access device, the bit line voltage will push up a little bit. You can see that in the pictures here if you want. But because the relative capacitance, this capacitance is pretty small compared to the capacitance of the bit line, as I say here. So the voltage swing is pretty small. And it just moves once and it doesn't keep moving because there's nothing keeping it moving. Once the cell gives up its charge or grabs some charge from the bit line, the voltage doesn't change anymore. So typically there's a very small change in tens or 100 millivolts, depending on how it's all designed. Right. So obviously things are better if we have more capacitance here, because that more capacitance here would lead to a bigger change on the bit line during the reading process, which means we could have a faster, more reliable reading process. Now, you also notice here that the process of reading the cell is destructive, right? After we read, we don't have we've lost the value that's inside the bit cell. Okay, so we have to do a write back after every read. So the operation of a read operation is actually read the value and then send it back, drive it back on the bit lines, and then do a write, right? Or keep the word line on and drive it. Once we sense a value, and send that value back on the bit lines, and then reestablish the value on the capacitor of the bit cell. So read operations are always followed by write back. The other thing, as I mentioned previously, is the cell loses charge over time. Okay, it leaks away, I say milliseconds here, maybe milliseconds. It's highly temperature dependent, right? Therefore, the cell needs to be refreshed occasionally. So DRAM chips have a controller on them where they go through periodically and just kind of cycle through all the rows of a DRAM block, reading and rewriting the value. So the way to refresh is just read it and then write it back. Or since a read cycle includes a write back, we just basically go and read all the cells or read all the rows, and that will refresh everything. Okay, that has to be done at a high enough frequency so that we don't lose any important values. Okay, so that's the basic operation of DRAM. This is really the way most DRAM chips work these days, and they're all over the place in laptops and cell phones and everything else. Now, I just wanted to mention something about the processing. I said that DRAM chips use special process. Therefore, we don't see DRAM blocks of 1T cells very often on logic chips like microprocessors. Like the large memory blocks on processors and other large chips will use SRAM. Because having special processing steps just for the DRAM would make them more expensive. It is possible, and there are companies that make so-called embedded DRAM which has a kind of some special processing steps for making large memory blocks, but it does increase the price, so it's not so popular. So if you look at the extra special processing steps that are, the other thing I should mention is the DRAM chips, the manufacturers like to make them as cheap as possible. So they add some processing steps to help make the DRAM capacitors, but they also take away some of the extra steps that are used more effectively for logic. And in fact, some wouldn't even have P-type transistors. They might only have D-type transistors to save on processing steps. So the way to get a higher capacitance in the DRAM cells, traditionally what was used is a trench cell. So in the processing step, in the steps of processing, the manufacturer would etch kind of deep holes at the location of each cell, and then put some dielectric down, and then put another conductor, and then make a capacitor. So this would make a very long parallel plate capacitor, you get a lot of surface area. If you try to make a big capacitance on the surface of the chip, it would just take too much area and the bit cell would be big, right? Which means we couldn't get many bits per unit area. Right? So if you can't use area, you can go in the other dimension, and that's the idea behind this trench cell, is that you dig a hole and build a capacitance on the sides of the hole, or the trench. For some reason, these got pretty hard to build, because you have to etch away this deep hole and get all these layers down into the hole, deposited somehow, right? So these days, and it's been the trend for a number of years now, to build so-called stacked capacitor cells. And you can see kind of in cross-section here, we build these capacitors up above the surface instead of tunneling down or making trenches down into the surface of the wafer or the die. These capacitor structures are built on top, and they're kind of built up with these fins, and the fins give more surface area, so we can get more capacitance. Right. So it's a fairly complicated process, but it's worked out so that now you can get a fair amount of capacitance per for each bit cell. So that's the processing. Now the only other thing I think about at DRAM I wanted to mention was the way the sense amplifiers work, and you could use a similar sense amplifier to what was done in the SRAM, but since these bit lines are equalized and set to VDD over 2, we can use another circuit that's a little more effective and also acts like a latch. This looks like a pair of cross-coupled inverters, right? Kind of mimics what we had inside the 6T cell, but here the power supplies, VDD and ground, are connected with these transistors that act like switches. So if these transistors are off, both of them are off, there's no power to this cell, right? And then when we turn those switches on, we power up the cell. And what it's going to do is go one way or the other, right? So if there's a slight bias when we turn the power on to the cell, that this right side is slightly higher than the left side in voltage, right? That will act like a 1, and the other side will act like a 0, and the cell will then snap its output to VDD and ground very quickly, right? So when we kind of balance, we get these, so the way this thing will work, when the precharge happens, we kind of set these internal nodes so they're all equal, and then allow these bit lines to affect, during the reading operation, these bit lines will change these voltages one way or the other, and then when we turn the power on with these switches, then the cell will kind of force a decision one way or the other. The positive feedback quickly gets it to a stable point. And you may have noticed when I was talking about the DRAM, it's not differential cells, it's single-sided cells. So what will happen is there'd be a dummy cell or a dummy bit line that, see, these will get put between two arrays of DRAMs, right? One will be activated and the other one will just act like a reference, right? And that gives us this other reference here. So then we can get this differential voltage between the bit line that's active and the bit line that's just being used as a reference from another array that's not currently being activated. Okay, so that was all the circuitry that I was going to talk about. And so I think at this point, you should have a pretty good idea about the difference between SRAM and DRAM and how the basic circuits work. So I'm going to talk next. Let's see what time we have. Okay, we have about 15 more minutes. So I'll start talking about memory blocks. And this is kind of bumping up a level. Assuming we know what's inside the blocks, how can we use those in useful ways in our designs? So let me go first with talking about multi-ported memory. So I'm just going to review this for a minute, just to remind you what a memory block looks like internally. There's all the bit cells that form an array. There's a row decoder, and then there's some circuitry for driving or reading the bit lines, and then for choosing subwords out of a row, or choosing words from a row. So the first thing is talk about is multi-ported memory. So the motivation for this is if you consider, for instance, the CPU that you're designing, and all CPU cores have this property, they all have a register file. And in order to make things go fast, you want to do more than one read at a time. Perhaps you want to do one read and one write at a time. This would be the requirements for the processors that we talked about in class. In order to execute an instruction and start a new instruction, every cycle you have to be able to read the two operands from the register file and write back the result of probably a previous instruction at the same time. So this is a little more complicated than what we were talking about a minute ago. What we're talking about a minute ago, those memory blocks, you could only read or write one word at a time. But here we want to read or write, maybe read two words and write another word at the same time. So that's common with CPUs. It's also common with, let's say, I/O buffering. For instance, let's say we have a connection to a network, or I show a disk here, connection to the CPU, and we'd like to be able to have kind of a dual porting idea where we can allow simultaneous access to this memory, the buffer. This buffer is acting like a go-between for the CPU and the disk. The disk might be streaming data off it for use later in the program, right? And so, but the CPU might be also accessing data from that buffer at the same time. So this kind of gives us a way to decouple the operations of these two, where the disk can be writing its data into the buffer at one speed, and then the CPU can be reading at its own speed. So we need access kind of simultaneously. We need two ports to this, right? So this is another reason why we might want dual-ported memory. And this type of interfacing function is quite common in digital designs, particularly when we're interfacing to external devices. So how do we build that? Well, if you look at, we can change the internal details of a memory block in order to accommodate multiple ports. Right. So if you look on the left, if we want a dual-ported memory, we can add another decoder and add another set of read and write logics down here and double up the bit lines and double up the word lines. Right. And the change in the bit cell would look like this. We'd still have the same, this is for SRAM, which is typically only done with SRAM, rarely done with DRAM. We still have a single pair of cross-coupled inverters here to store the bit value, right? But we'd have two pairs of bit lines, bit 1 and bit 1 bar, and bit 2 and bit 2 bar, right? And then two pair of, or two word lines here. One that correspond to the outer pair of bit lines, and one, the lower one, that corresponds to the inner pair of bit lines. So what this means then is we could have each decoder here have a different address, right? And so this grayed out decoder here is activating the lower bit word line, and the white decoder here on the left is activating the upper word line, right? So each decoder could be activating a different row. So we can have more than one row activated at a time, but the values don't get confused because they're going to use different sets of bit lines. And that can all get sorted out by having two different sets of logic here on the periphery at the bottom. Right? So it's kind of funny. It's about the same amount of circuitry as two different memory arrays, right? Because the only thing that actually gets shared is these two inverters here. But we do share those inverters, and so there's some savings. So we can extend this scheme to more ports if we want. But I mentioned earlier, when designing this SRAM cell, we have some constraints about the size of the transistors in the inverters to these access devices, right? And if you add more ports, it becomes harder and harder to build to meet all those constraints of the sizes, right? So the scheme really extends maybe to one more port. And after that, then we use some other different kind of scheme to get multi-porting. But this is the simplest way to do it. So I thought I would show you that. Okay, so the next thing I want to talk about is what we can do to combine memory blocks, right? So what I showed you previously with this memory architecture, or this one here, is really, you can think of that as a building block. It's hard to build a very large memory this way, because if we had a really large memory, like 1,000,000 bits, this cell array would get so big that we would have a lot of delay on the word line and the bit line. Right? So we want to kind of partition this, a bigger memory into smaller memory blocks, and then combine those with multiplexers and other things. So I'm going to show you that, how we would do that typically. So here's just one basic idea. So if we're going to design a large memory, you do something like this. We could have different subarrays of bit cells, right, with periphery circuits interspersed. Right? So for instance, the sense amps could be here, and decoders could be here, right? And then the leaf array might be limited to 128 by 256 or 256 by 256 or something like that. The other nice thing about this is that by doing it this way, we can reduce the power consumption by only activating whatever array is currently being accessed. And the controller and the decoders can figure out which ones to activate. Right. So so what would happen then, if the word we're looking for is stored in this array, we'd activate that array. This decoder would turn on the right row, and then the I/O circuitry would kind of pass the value out to the outside that way. Okay, that's the basic idea. There's a lot of details I'm not telling you, but you should understand that we kind of use this kind of partitioned approach. Okay, but I'm going to show you more details about how we can actually, kind of working from the bottom, actually. That was kind of top down. The other way to think about it is the bottom up approach. And this really tells us the principles behind how do we cascade memory blocks to make larger memory blocks out of smaller ones, right? And so here's a principle. So first, if we want to increase the width of a memory, so for instance, let's say we're given a 1K by 8 memory and we want a 1K by 16. Okay, so again, to remind you what this means this is a memory that stores 1,000 words, 8 bits wide each. But let's say that's our building block. But what we want really for our application is a memory that's 1,000 words deep, has 1,000 words in it, but it's 16 bits wide instead of 8 bits wide. Right. So how could we do that? Well, imagine this is our 1K by 8 bit wide memory. Okay, and it has 10 address bits because we need 10 address bits to address 1,000 different words, right? Because 2 to the 10 is 1K. Here's a write enable signal. There'd be a clock that comes into here too. Here's the data in, and here's the data out of this memory. So this is 8 bits because it's data in. We said it's a by 8 memory, and then the output is 8 bits because it's a by 8 memory, right? So we could either read or write this. If we wanted to use this as a building block to make a 16-bit wide memory, we can do that by using 2 of these in parallel, right? It's a pretty simple concept. We just instantiate another one of these blocks. And then we can combine these 2 D outs to make our output word of our bigger block, or 1K by 16 block, and kind of combine these data ins to make the data input of the larger block. And the address lines we then just need to tie together, right? So we do it like this. So the write enable for the bigger block connects to both write enables. And the address lines are just all shared, right? So when we write a particular word in this memory is going to hold the low bits of the word, and this memory will hold the high bits of the word. Right? Actually, I have it backwards. The bottom one is the low bits, and you can tell by how I labeled the bits here. Right? And the top memory holds the most significant bits, the bits 8 through 15. Right, so that's a pretty simple concept. We can just put memory blocks in parallel to make wider memory block out of less wide or narrower memory blocks. Right, so we can, let's say we want to increase the depth of a memory. Right. So again, let's say we're given this 1K by 8 memory block and we want a 2K by 8. Okay, the width will stay the same, but we want to make 2,000 locations, storing 2,000 words instead of 1,000 words. This is a little more complicated, but it's not too bad. Again, here's our memory block, and this memory block can hold 1K, so we need to find a way to hold 2K, so obviously we're going to need another memory block, and it's just the only difference from the previous example is how we're going to connect things up. So there's a memory block. Now, if we're going to go to 2K, we're going to need an extra address line, right? Because 10 bits is only enough to address 1,000 locations, right? So the way we're going to arrange things is that one of these memories will hold the first 1,000 locations, or first 1,000 words, and the second memory block will hold the second 1,000 locations. And we're going to add an extra address line, which we can then use to distinguish between this block and this block for both reading and writing. Right. Okay, so that's what I've done here. We have another address line here, A of 10. Okay, so A of 0 through 9 gets connected to both memory blocks. And then we use the top bit of the address. We've added an extra address line in order to accommodate 2K locations. It gets used two different ways depending on whether or not we're reading or writing. If we're reading, we can use that to control a multiplexer that sends the proper, and this is an 8-bit wide multiplexer, we can send the proper word out. So when we read, we're going to read out of both memory blocks, and then we'll choose the proper word according to what A10 is. So if A10 is a 0, that means we want that word we're looking for is in the lower half of the address range. If A of 10 is a 1, that means the word we're accessing is in the upper half of the address range. So it will be the one coming out of this memory. And so we'll choose that with the multiplexer. And the other one just gets discarded. So we wasted some energy by doing the read. If you're very tricky, you could control the power. You'd use this address bit to just turn on whichever bank needs to be accessed and therefore save energy. But I didn't do that in this example. I just used a simple multiplexer here. That's the reading. And the writing, similarly, what we need to do now is take our write enable signal and it with this address line. So we're going to write enable the proper memory block based on what this address bit is. So if the address bit is a 1, that ANDed with write enable when we're doing a write will produce a 1 for the write enable into this block. If it's a 0, then we'll activate the bottom block. That's why there's a bubble there. Okay. So this gives us twice the depth by using 2 memories. If we use 4 memories, we could extend this idea and make it 4 times as deep if we wanted to. But to make it 4 times as deep, we'd have to add another address line, of course. So every time we double the size of the memory, we need to add another address line because we can access 2 to the number of address line locations in the memory. Okay, so 1 more minute. So let me show you just this and then we'll continue next time. So actually, I think maybe we should stop since I don't think I can do it in a minute. We will continue this after the break. Just to remind you, in case you forgot, in all the chaos, next week is spring break. So I won't be here to give a lecture. But if you need to contact me for anything relevant to the class or anything else, you can do that and send me mail, and I'll be around. I'm not going anywhere because I'm sheltering in place. So I hope you all have a good spring break and everybody stays healthy. And I look forward to seeing you in 2 weeks. So take care. See you later.